In case anybody was wondering, the answers to the important questions in life, the Stay Puft Marshmallow Man won the race. So just because again, important stuff. It's going to take me a little while to grade the exam. My goal is next Monday or next Wednesday, but I'll be blunt. I want to get it graded, but I'm not in. I've got like other stuff to grade too. So I've got some submissions in another class that I kind of want to knock out first. So there we go. The only other thing, I don't have this on the slide, but I did want to mention this. Next Wednesday, the 30th, I won't be here. So I'm canceling class that day. And what I will most likely do that day, I usually will like pre-record a lecture or something like that. But given the fact that the tail end of the class is just going to be a review, I'm taking a look at my lectures, and I genuinely might just cancel class. So, like no homework, no, just take a break. So, because we've got room in the schedule to be able to do so. So, I just throw that out there. Okay, I'll keep you posted though. If we do something, it will be very minimal. Okay. So what we're going to do today is move on from moments, kind of, okay? We are going to start a new topic in the class. And I want to talk a little bit about the motivation, about what this topic is. And I want, hopefully, by the end of today's lecture, well, definitely by the end of today's lecture, you'll understand what the term centroid even means, okay? But I want to preface this by saying that in an odd way, I don't really have anything left to teach you this semester, okay? What I mean by that is, if you were to tell me what this class is about, it's about forces and moments. That's it. Exam 1 was all about forces, and Exam 2 was all about moments. That's it. That's really all there is in Engineering 213. What we do in here, though, for the rest of the semester, though, is we take those concepts of forces and moments and we apply them to classical problems in engineering, okay? And one of the most fundamental applications of the principles of statics is to locate the centroid of a given area. And you'll understand what I mean by that as we get into the lecture. But maybe I want to take a step back and get a little, like, real basic, okay? So let's say I were to give you a square. That's pretty basic. And I said, where's the center of that square? Does everybody feel confident in locating that? Yeah, it's right there, What about the center of a circle? Pretty easy, right? What about the center of that? And maybe a better question would be, like, what does the center even mean? Like, if I use the term center, like, what does that word even mean when we're talking about some arbitrary cross-section like this? I mean, I could define the center of a circle really easy, right? Because, how do you define a circle? A circle is the set of all points that are all equidistant from a fixed location, right? And that fixed location is the center. That equidistant, that's the circle, right? You could define a center of a square pretty easily, like fold the center and square in half this way, fold it in half this way, the intersection, there's the center, right? But what does that even mean for this? It doesn't work, There's no precision in that definition. So we need to redefine that. And so what we'll do is we don't even use the term center, we use the term centroid. And we're going to define this rigorously later here in a bit. Now, this is like what I've got here in this slide is something that you might find in a discussion in middle school, you know what I mean? So like, why do we as engineers care about locating the centroid? Well, the reason why is engineers often they deal with shapes that aren't what I'll call easy shapes. There are plenty of instances in the real world where engineers have to assess structural stability, have to assess dynamics, have to assess just the safety and the reliability of systems that involve irregular distribution of forces on bodies. Let me give you a couple of examples. This is a dam, right? Okay, and often when we're looking at engineering problems, we will look at them from a cross-sectional standpoint. So this is me taking the samurai sword or lightsaber through the dam and looking at the dam like this. And this dam is not an easy shape, right? It has curvature to it. There's fluid acting on it. That fluid also has a curved shape to it. So how do we assess the equilibrium of that? Okay. Here's another one for you MEs. Okay. Lift on an airplane wing. How do we define the forces and moments on this wing? How do we do that, and how do we do it precisely? Well, we have to relate them from a point or from a fixed reference that we can all find. You know what I mean? So whether we're in civil engineering land, mechanical engineering land, biomedical engineering land, understanding how to locate this frame of reference, this point, which I'm going to call the centroid, is we have to do that to be able to define the forces on the body, because once we get that, then we can start assessing equilibrium and so on and so forth. I mean, up until now, we've already started to dip our toes into this a little bit. I mean, like for example, we've had problems where we've had, like a sign that was held up by a cable, and we had that the sign weighed 270 pounds, and we would place that force as a vector in the center of the sign. But what if the sign wasn't rectangular? What if it was something like this or something like this? How would we go about it? Okay, that's kind of the idea behind what we're talking about. Okay, but I've been using all this terminology. What's a centroid? What is a centroid? Okay, so let's take a step back. Okay, so let's say that I have some plate. Okay, and it doesn't matter what the plate looks like. It really doesn't matter. Okay, let's just look at it like this. Okay, and let's put a coordinate system on this. Okay. Okay, so we'll call this, I don't know, X and Y. Okay, and we'll say that Z goes this way, right? So the Z axis goes this way. Okay, and the plate is cut up into a bunch of elements. So think like a grid, going this way, a grid going this way, and so on and so forth. So let's just pick one of those elements. We'll call this element right here. This is an element of the plate. Okay? And we're going to look at this element, and we're going to try and characterize some things about this element. Okay? So we're going to say, okay, where is this element? Let's start off, where is this element? We'll reference the location of this element by its center. We'll go ahead and use that term now. And we'll say that center is X1, Y1, whatever the point is. It doesn't really matter, okay? And this is a plate, right? So again, if I were to look at this element like this, right? So this is that shaded side, but the plate also has a weight to it, right? Does that make sense? Okay, and by the way, if we wanted to determine the weight of that plate, what we would say is the, maybe, I don't know, the area of the plate times, I don't know, its thickness times its unit weight. The unit weight being the unit weight of the material, right? So the unit weight's sort of like density, but density is a mass per unit volume, unit weight is a weight per unit volume. But I'm getting ahead of myself. I'm just wanting you to get the kind of idea of what I'm talking about here. Okay? So far, so good? Okay, so the thing is, though, there isn't just one element, right? If I'm breaking this up, there's an element here, an element here, an element here, an element here. There's all these all over the place, right? So if I wanted to determine, let's say, the total weight in the plate, I would say that the total weight in the plate is just summing up the weight of all these individual elements, right? Everybody with me on that? So we'll call that a sum of forces, and I'm saying it's a sum of forces in the Z direction, right? Because we'll say the weight goes this way, right? So this is just sort of me in the helicopter looking up, and so the weight goes up and down. So if I wanted to sum up the weights, I would say the summing up the weights would be delta 1, or delta W1 plus delta W2 plus up to however many elements that I have. And by the way, you all know from Calc 1 that the more elements that I have, the better the approximation would be. So if I set the limit as the size of these elements approach 0 and then sum them up, I'm getting into integral land, right? That's kind of what we're talking about. We're going to get to that here in a bit. Okay, Now, not only am I going to sum forces in the z direction, but I'm going to sum moments. And I'm going to sum moments, I'm going to erase these, by the way. I'm going to sum moments about the x and the y axis. Now, it's going to look here like I got a typo here, but I don't. Okay? So, I've got here that the sum of moments about x equals y times delta w, y times delta w, y times delta w. Why is that flipped? Okay? So if I'm summing moments about the x-axis, right? So let's think about this. Okay? So I need the force times the shortest distance from the force in question to the axis. And if this is the x-axis, how far from the x-axis is this point? It's y1, right? So there's a flipping there, right? So if I'm summing moments about the x-axis, I take each of these terms and I multiply them by y. And likewise, if I'm summing moments about the y-axis, I take each of the terms and I multiply them by their x-coordinates. Does that make sense? All right. Everybody with me so far? So again, notice that flipping, okay? All right. So far, so good? Okay, now, what I want to do is I now want to locate the center of gravity. Everybody's heard that term center of gravity, right? There is a difference between the term center of gravity and centroid. And we'll get to that here in a bit, but bear with me. All right, so the first thing I'm going to do is I'm going to locate the center of gravity. Now, what do I mean by the center of gravity? Okay, well, I propose that the weight, the total weight of this plate is just going to be the sum of, here, let me do it like this, the sum of all those individual weights, right? So far, so good? Now, what I would like to do, here's what I'd really like to do, okay? Because you all know by now that if you want to start writing forces and moments and you want to start doing cross products and all that hullabaloo, okay? You all know that if you want to do that, here's what you need, okay? You need to figure out where this point is, okay? What do I mean by this point? I want to be able to put my total weight right here, okay? And I need to figure out where do I put it, okay? So I'm trying to figure out specifically what this distance is, which maybe we'll call y center of gravity. And I need to figure out what this distance is. We'll call this x center of gravity. I need to figure out where that point is so that I can replace all those little delta w's with a single vector. And I want to figure out where that point is so that it has the same effect as all those little itty bitty pieces. Okay? So here's what I'm going to do. I'm going to say, what if we wanted to idealize the plate as a single vector? So we're going to figure out where that point is. Okay? Basically what we're doing is an equivalent system. I mean, think, if I had idealized this plate as 20 delta w's, and I take those 20 delta w's and I replace them with a single vector that has the same force and moment equivalency, isn't that an equivalent system? Isn't that the same thing we did back in exam 2 land? So what I'll do is I'll say, okay, instead of writing mx as y delta 1 plus y delta 2 plus y delta 3 plus y delta 4, I'm going to say, let's write it as the total weight times this coordinate. And the same thing with moment y, times the weight times this coordinate. And now what I can do is I can solve for these coordinates pretty easily. Okay? So basically what I'm saying is I'm saying that this center of gravity is the sum of these moments divided by the sum of the weights. And the same thing for y, right? The same thing for y. So y times delta w over delta w. Essentially what I am doing is I am computing a weighted average. Okay? This is sort of a physicist's way of explaining weighted averages in statistics. Basically, that's what we're doing here. Okay? And I propose that this expression, the sum of x times delta w divided by the sum of delta w, or the sum of y times delta w over the sum of delta w, will tell you where the center of gravity is. Okay? There is a difference between the center of gravity and the centroid. And we're going to get to that here in a bit. But does everybody kind of get the idea so far? Everybody with me so far? Okay. So, first off, before we get into the center of gravity versus centroid land, I think there's some of you that are probably like, wait a minute, Dr. Mike, if you have a plate that looks like this and your elements sort of look like that, isn't your estimate going to be a little off? Because like you've got this weird boundary. So what do you have? Like this, and then you've got some overlap here and so on and so forth. So the grid is going to overestimate what the plate looks like, right? Well, what I'm going to do is I'm going to take those delta W's, I'm going to make them smaller and smaller and smaller and add them up. And so basically what I'm going to do is that just leads to integrals. So instead of writing this times the sum, I can also write it as an integral, right? I can say, okay, bless you. The weight, I'm just going to say, is integrating that region. And then x bar, or x for the center of gravity, and y for the center of gravity, is just this fraction. The weight on the bottom and on the top, those moments. X times dw, y times dw, just integrating. Is that a stretch? Is everybody okay with that? Everybody okay with that? Okay. I mean, it's just a Riemann sum, if you remember that from Calc 1. Okay. Now, that's good, great, grand, and wonderful, but that doesn't get us to a centroid. That doesn't help us, okay? Let me tell you the difference between a center of gravity and a centroid, okay? The thing about the centroid, well, let me say this. The term center of gravity works very well for systems that have variable unit weights or variable thicknesses. So, as an example, it would not make sense to ask somebody what is the centroid or where is the centroid for a Honda Civic. That wouldn't make sense, okay? Because the Honda Civic is made of steel and aluminum and fabric and tires that are made of rubber and copper wires and the gasoline, the fluids, all that stuff, right? So because the Honda Civic is made of all of these components that have different sizes and different weights and unit weights associated with them, asking somebody where the centroid of a Honda Civic is doesn't make sense. Asking them where the center of gravity of a Honda Civic, that's totally fine, okay? Often though, in the design of that Honda Civic, you're not just solving an equation and boom, there's the Honda Civic. You're designing each element one at a time, right? You're designing the transaxle, the piston, the so on and so forth, each individual component. And each of those components are of uniform thickness or can be considered as such and of uniform material. So here's my point, okay? The delta W's are basically going to be the areas times the thickness times the unit weight. And I propose that if you are dealing with an object that has consistent unit weights and consistent thicknesses, you can factor all that out, okay? So here's my point. So if you go back to this expression for center of gravity, everything has a gamma and a thickness. Everything has a gamma and a thickness. Gamma is that lowercase y looking thing. It's the lowercase gamma. I propose that if you are dealing with bodies, or you can consider them, those bodies of uniform thickness and of uniform unit weight, you can factor those terms out and cancel them. So instead of dealing with a weighted average considering weights of the plate, you can now be looking at a weighted average in terms of areas, okay? And it stops becoming a problem about dealing with weights. It instead becomes a problem dealing in just areas, okay? And I propose that this is the definition of the location of the centroid. That the center of gravity is a weighted average where you are looking for just that, the weighted average of the weights. Whereas the centroid is a weighted average of the areas, okay? So you are only looking at the area geometry. Okay, so like what we're going to do here in a bit is we're going to take this region right here, this curve that's bounded by the parabola y equals x squared, and we're going to say for this region, where is the centroid? Okay, we're going to do this here in a little bit. And my apologies, this is way not to scale. My artwork is horrible, but you'll get the idea. So, what we're going to do today is derive some expressions for the centroid, and that's what you're going to have on your homework. This is going to be our first and one of only true real forays into using calculus in this class. So we are going to be doing a little bit of integration in here. But the integration is really basic, it's really straightforward, but we are going to be doing it. Okay? A lot of times what we will do in practice is we will have problems like this. So I'll give you a plate like this and I'll say, okay, tell me where the centroid is. And in practice what we'll do is we'll take this plate and we'll break it up into a rectangle and a triangle and a triangle. And we can look up where the centroid of a triangle is, or the centroid of a semicircle, or something like that. We can look those up. And that's what we will do later. But for now, I want you to understand what those references are and what they look like. So I want to, in order to do that, I want to kind of use our integral expressions. Instead of integrating in terms of weight, we are going to integrate in terms of area. Okay, and I'm going to show you how this works with the example that we're about to do here in a bit. So let's look at this example. Let's break this out. Okay, so I have here this bounded region that's bounded from the x-axis to the curve y equals x squared. Okay, and what I want to do is I want to determine where the centroid is. And by the way, just so that we're all clear in terms of centroids, if this is a uniform if this body is of uniform thickness and of uniform density or uniform unit weight, then if I went down to the 3D printer and printed this shape out and balanced this shape where the centroid is, it would totally balance, right? Because all the moments essentially would cancel. That's the whole idea. So we're trying to figure out where that point is. Okay? So we're going to have to break out a little bit of calculus. Okay? And what we're going to be doing today is essentially this. So we're going to be figuring out where x bar is and y bar is. Okay? Now, x bar is going to be the integral of x dA, and this is going to be the integral of dA. This is going to be the integral of y dA over the integral of dA. And so some of these terms look a little, I don't know how to put this, they maybe look a little abstract, like what is the integral of dA, like what is dA and how are you doing that? Don't worry, I'm gonna show you that here in a little bit. Actually, I'm gonna show you that right now. Okay. So let's see what we can see. Okay. So. Okay. All right. Let's start off with something basic. Okay? Let's start off with the area. Okay? Now, the area is going to be defined as this, but I want to take a step back and see if we can maybe define this a little bit rigorously. So let me show you what I'm going to do here. This is going to maybe feel a little familiar from Calc 1. Hopefully it feels familiar. Okay. All right, let me see if I can. All right. So what does the curve look like? Looks like this. So we're doing the curve y equals x squared, okay? And we're evaluating that from x equals 0 to x equals 3, okay? All right. Now, when I write the term integral dA, what I'm basically saying is that I'm summing up these little elements of area, right? So do you remember how you did this in Calc 1 or how you described this? What you would do is you would say, okay, I've got a little sliver of area here, right? And I would call this dA, and I would sum those up, right? So how would you do that, okay? Well, I seem to remember that the width of those elements was dx. Wasn't that the case? The width is dx, and that the height of these things, what is the height? The height, we would say, is y, right? So would you agree that dA is just going to be y dx? Does this sound familiar to stuff that you did in Calc 1? Y'all seen this stuff before, right? Okay, and then y in this case is x squared dx. So far so good? So if I wanted to determine, let's say, the area, what I would do is I would essentially integrate that, right? From x equals 0 to x equals 3 of x squared dx, right? And hopefully by now this is a very straightforward calculus problem. What is the integral of x squared, by the way?
X cubed over 3.
There we go. And so plug in the top number minus plug in the bottom number, and I'm going to get 3 cubed is 27 over 3 is 9. So I'm going to get an area of 9. Is that fair? Okay. Now, with this definition, what I can also do is I can also develop the following term. I can say, what about the integral of x dA? Now, why am I doing x dA first? Because I'm able to write dA in terms of x. Okay? So I could say, what about x times, oh, let me do this. What about the integral from x equals 0 to x equals 3 of x squared dx? Again, I'm doing the x first because that's written in terms of x. Now, I am going to come up with a name for this, by the way. I'm going to call this QY. Okay? So, whoop, keyboard popped up. Okay? This term Q represents the first moment of area, and the reason why the subscript is Y is because of the same thing that we did over here, right? Remember, like, if I want to find the X coordinate, right, the distance from is Y and vice versa, so I'm flipping the axes, so I'm doing the same thing here. So this is going to be the integral of x to the third dx, which is, I think that's x to the fourth over 4. Did I do that right? And some of you might be wondering, isn't he getting a little, like, notation happy because he keeps putting x's on the top? Like, why do you have to put x equals 0 and x equals 3? Trust me. You'll see. You'll see. So, and so this will be QY equals, what is that, 81 to the 4, or 81 over 4? Okay. Is everybody okay with this? Everybody okay with this? Okay. So if that's the case, then I propose, here's what I propose. I propose that our X bar is going to be QY over A. And if you don't like this notation, then basically what you can say is it's just the integral of X dA over the integral of dA. And again, all this is just a weighted average. It's just a weighted average written in the integral form, right? So this is going to be 81 over 4 divided by 9. Okay. Okay. So here's what we're saying, that here's this shaded region. Okay, here's this shaded region. And I'm trying to find this point where the whole thing balances. Okay? I propose that the coordinates of that point are 2.25 comma something. We haven't figured that something out yet. Does that point kind of ring true? I mean, would this make sense if this was 7.25? Would that make sense? No, it's got to be somewhere in here, right? So it being 2.25 shouldn't be all that scary, okay? Now I am going through the calculus part of this pretty easy. I mean, I guess I just want to make sure. Is this comfortable with you all? Is this not going too fast on this stuff? Everybody good? Okay. All right. So here's what I want to do now. Let me take a step back. See, does anybody need any time to write all this out? Everybody good? Okay. Here's what I want to do now. I want to do this again. Let's do that better. I want to write this now in terms of y. Okay. Let's see. All right. So how is that going to work? How's that going to work? Well, let's see. Okay, so let's look at this region again, but let's look at it a little differently. Okay, so first thing, let me move this over a little bit. Let's now look at it in terms of y. Okay, so before we integrated this region from x equals 0 to x equals 3. Now I want to look at it in terms of y. So we're going to go from y equals 0 to y equals 9. Okay, so we'll say from y equals 0 to y equals 9. So by the way, you can probably start to see this is why I wrote the integrals that way, because I'm going to write them now in terms of y. Okay, so what I'm going to do is I'm going to now see, bless you, I'm going to see about defining the slice this way. Okay? And I've got to do this if I want to get y bar. Okay? So let's see if we can do that. Okay. All right. So let's see what we can see. First off, what is this thickness going to be? dy. Is that fair? Okay. All right. Let's talk about this. I propose that from the origin to some arbitrary point on the curve is going to be expressed by some distance or some term x, right? That if I want to get from here to here, that's x. Well, if that's x, what is this? Huh? What is this distance if this is x? 3 minus x, that's 100% right. 3 minus x. So therefore, okay, and by the way, let's just make sure that we're aware of one thing. If y equals x squared, x is the square root of y. Are we all in agreement with that? So, I propose that dA is going to be 3 minus x dy. Is that fair? The width times the thickness? Is that fair? And by the way, this is going to be that, right? Is that right? Now, is there a way that we could test whether or not that definition is correct? I can think of a way. How about this? How about let's just see what we get. Now you're starting to see why I did the y or the x equals. Now I've got the y equals because now we're integrating in terms of y of doesn't that work or will it work? Well, let's see. What is the integral of 3 going to be? 3y. Minus, okay, what about the integral of y to the 1/2?
Negative 1/2 y to the 1/2 power.
Well, we do, no, hold on. If you have, hold on, let's see. If you have the integral of x to the n dx, right? So this is going to be y to the 3/2 over 3/2. Is that right? It's not a reciprocal. Yeah. So this is going to be evaluated from y equals 0 to y equals 9. Is that right? Okay. So okay. Plug in the top number minus plug in the bottom number. What happens when we plug in the bottom number, by the way? 3 times 0 minus 0. So this is going to be 0. Okay. By the way, 9 to the 3/2 is, what is that? The square root of 9 cubed. So that's 27, right? So this is going to be 27 minus 27 times 2/3, or 27 minus 18. Isn't that what we got before? Isn't that a way of testing whether or not your definition works? That make sense? Now, why did we need this, by the way? Why did we need this? Well, the reason we need this is because if we want to get this, right, if we want to get the other point, we need to be able to evaluate that. So in order to be able to evaluate this, we need everything written in terms of y. So that's why we needed the dx and the dy the other way. Okay. So, okay. You didn't expect like Calc 1 all over again, I guess, today, did you? Like, we are on this side of 3rd Avenue, Dr. Mike. We are not over there. You betrayed us. When we have folks in here that don't know who the Stay Puft Marshmallow Man is, what happens? I'm just kidding. I'm kidding. Not really. Okay, so 3 times y, 3y. Here, I'll remove that. 3y minus, okay, let's see if I remember my algebra here. So y times y to the half is y to the 3 halves. Okay. Let's see if I remember this. Okay, so what's the integral of 3y going to be? 3 over 2y squared. There we go. All right, and then this one, okay, so 3 over 2 minus, I'll scroll this up a little bit. Okay, y to the 3 halves. So it's y to the 5 halves over 5 halves, right? Or that, right? Evaluating, I just flipped the fraction there. So y equals 0. And then if I plug in the bottom number, I'm going to get 0 everywhere. So this is going to be 3 halves times 81 minus, okay, so what do we get here? We get 2/5. Let's see, 2/5. So 9 raised to the 1/2 is 3. 3 to the 5th. Okay, you want 243? Does that sound about right? So I think when this is all said and done, you're going to get that QX is 243 over 10. We can test that out if you want, because we can say, okay, this is going to be 15 over 10 times 81 minus 4 over 10 times 243. So this is going to be 15 times 81 minus 4 times 243 over 10. And I think if you plug that in, you'll get 243. Okay. So therefore, here's what we can do. We can say that y bar is just that, or if you don't like that notation, YDA. Which is going to be 243 over 10 over 9. Move that up. Kind of hard to write like that. Okay, so 243 over 9. So that's just going to be 27 over 10. So and that's our answer. So this right here would be 2.7. Does that kind of make sense? Just like the 2.25, that's about where the centroid is. Here's a random question just to see what everybody thinks about this. Does the centroid of a shape have to be on the shape? Do you think that that's the case? I'm thinking of Homer Simpson and donuts. Where's the centroid of a donut? In the hole, right? Not necessarily, right? The centroid doesn't have to be on the shape. Just something to think about.
Just within the perimeter, like there's.
Well, not necessarily even too. That's a good question. You said within the perimeter. I know of certain angle cross sections where the centroid's right there. It's a good question. That's possible too. So we'll get to that later though. Food for thought, right? Food for thought. Okay, any questions on this? All right, I want to show you something real quick. So I have a sort of a homebrewed assignment for you. This is your assignment. I want you to derive the coordinates of this centroid, okay? This is a triangle, right? I want you to figure out where the centroid is. It is on the shape. It'll be somewhere about right here, okay? And the centroid, I think when you do the algebra, you'll find it. You can kind of see what's going to happen. I'm giving you a hint, or two hints actually. So the first hint I'm giving you is tell me what the equation of this line is. And if you need help with that, think about what is the slope of the line and what is the y-intercept of the line. And then the second thing is while you're integrating, it's going to be alphabet soup. Treat the b and the h as constants, okay? The only thing that are variables are integrating in terms of x or integrating in terms of y, okay? So, sound good? Okay, so I'm going to pull up the code one more time. I will see you all on Wednesday.